Hi guys, welcome to the lecture for class number 4. This class is going to be about tectonics and volcanism, and we're really going to look at a few different types of volcanoes. And volcanoes are interesting for a few different reasons. For one, they're a really important link between some of the deep earth processes we've been talking about so far, like mantle, convection, and magma chambers, and they link those things to the surface through the eruption of lavas and also the emissions of gases that have a big effect on global climate, among other things. So that it's a pretty important piece of the kind of global tectonics process. Relevant to society, they're also a really important source of geothermal energy. A lot of countries that have a lot of volcanism make a lot of their electricity from geothermal, and we'll look more at that in future classes. And then, of course, volcanic eruptions present hazards. They're dangerous, they kill people almost every year. So we'll use that hazards angle to motivate this lecture a little bit, and I'll start out by posing the question, which of these two towns is in more danger from its nearby volcano? The first town being La Fortuna in Costa Rica, which sits at the foot of this Arenal volcano. And you can see a picture of it here smoldering ominously above the town. Second volcano is, second town is Hilo, Hawaii, which sits on the coast here, also at the foot of the volcano Mauna Loa. And here's that town of Hilo with Mauna Loa in the background. So obviously we've got a lot of human infrastructure built right up against these volcanoes, and it's reasonable to ask the question, are these towns in danger? And if so, what do those hazards look like, and how can we mitigate them? And so I'll give you kind of a preview of the answer, and that is that both towns are in danger, but they're in different types of danger. In Costa Rica, this is a stratovolcano that could violently erupt and blanket the town in ash and debris, whereas in Hawaii, this is a shield volcano that could erupt a long-traveled lava flow that might come down and actually bury the town of Hilo. So a preview of the answer to this question is that both towns are in danger, but different types of danger. La Fortuna in Costa Rica sits at the foot of what's called a stratovolcano that might violently erupt a cloud of ash and hot debris, burying the whole town from the air. In contrast, Hilo sits at the foot of what's called a shield volcano, which is unlikely to erupt catastrophically, but could easily vent out a high volume of very hot basalt magma that could flow a long distance and actually bury the town in lava flows. So in this lecture, we'll look at why we know the hazards are different and try to understand why they're different. So where are we headed in this lecture? First, we'll look at where volcanoes occur, subduction zones, hotspots, and mid-ocean ridges. Then we'll look at the properties of basalt versus rhyolite magma. And we'll look at properties of shield volcanoes versus stratovolcanoes. So the first volcano location we'll look at is a subduction zone. And we talked about this a little bit in the last class, and we can quickly review what we talked about. Subduction zones are places where oceanic crust goes down beneath continental crust, and often this is actually driven by downwelling of mantle convection. So there's a dense mantle flow where mantle material is sinking back deeper into the mantle and bringing that sinking plate with it. And this has the function of returning oceanic crust into the mantle where it will be melted and reintegrated into the mantle, but also we're going to melt a bunch of the silica-rich minerals along the way, and we're going to generate new continental crust as that silica-rich felsic magma ends up getting emplaced in the crust. So let's look quickly at this animation, and we can see the exact things we're just talking about. Down goes the oceanic crust. Here the melting is occurring once things get hot enough at depth. Those magma plumes are rising, and importantly, those magma plumes are actually feeding volcanoes at the surface. So today we're really going to focus on aspects of these surface volcanoes. So a great example of the link between subduction zones and volcanoes is South America. You can see this trench here, this deep offshore topography, that's actually a subduction zone trench. So the Pacific plate is coming in and diving down under South America here. And each of these red dots is actually a volcano, an active volcano. For example, the Villarrica volcano here in Chile. And as we talked about in the last class, a key attribute of these volcanoes is that they erupt magmas of a felsic composition, for example, rhyolite. So a second location where we find volcanoes are at what's called hotspots. And a great example of this is Hawaii. So hotspots are a little different. The magma at a hotspot is actually generated very deep in the mantle, perhaps thousands of kilometers depth, and then it makes its way up in a plume, penetrates through the crust, and erupts on the surface. In this case, in the volcano Mauna Loa in Hawaii. Now, what's different about this in particular is that because the melt is coming from a deep mantle location, it's actually fixed relative to the overlying tectonic plate. So in the case of Hawaii, the Pacific plate has been moving to the northwest over time, but the hotspot's been staying in the exact same place. So the result is that we get this track, basically, across the Pacific. The current volcano is here on the big island of Hawaii, and all of these islands are older volcanoes that were erupted millions or even hundreds of millions of years ago. And what's really cool is this track of volcanoes actually records a shift in the direction of the Pacific plate right around 80 million years ago. Another important aspect of hotspot volcanoes is that they erupt magmas of mafic composition. So most commonly this would be a basalt. And that's very different than what we see at subduction zones, where we get felsic magmas. So a third location where we find volcanoes is at mid-ocean spreading ridges. And we've already talked about these quite a bit, but we haven't really thought of them as volcanoes. But of course, that's exactly what they're doing. We're melting the mantle, it's making a magma, and that magma is being extruded at the surface. By definition, that's a volcano. What's a little bit different about spreading ridges is that, of course, that volcano is erupting underwater, so we don't see any direct evidence of it unless we're able to take a submersible vehicle all the way down, where you might find something like this. This is called a black smoker, and it's a place where hot gases and liquids and magma are being released from active volcanoes along the mid-ocean ridge. So this was from a recent New York Times article, just came out about a week ago, and you can see each of these dots represents a particularly active epicenter of volcanism along a mid-ocean ridge. And as we've already learned, volcanoes at mid-ocean ridges also erupt magmas of a mafic composition, specifically basalt. So if we bring all this together, this is kind of a simplified tectonic map of the United States. And what you can see is major tectonic boundaries are shown in blue. Those are subduction zones. Spreading ridges are shown in yellow or gold here. And each red dot represents a volcano. So of course, one of the things you'll see right away is the link between volcanoes and subduction zones. This extends from Japan up through the Aleutian Islands in Alaska, of course, Pacific Northwest in the US, Costa Rica, Guatemala, and then all down through South America. So those are all subduction-related volcanoes. Likewise, we've got a few scattered hotspots. Here's one in Hawaii. And then if you look at some of these dots sitting out in the middle of the ocean, many of those are also associated with hotspots as well. And then we've got our spreading ridge volcano, Iceland, which we talked about in the last class. So the second part of this lecture, we'll talk about what are the differences between basalt and rhyolite magma, and then ultimately how does that influence the properties of the volcanoes that they're associated with. So one really important aspect is that basalt is really fluid, and it comes out very hot and can flow long distances, sometimes hundreds of kilometers in these rivers of lava. Almost always that's going to be basalt. And typically basalt volcanoes erupt non-violently. They might spew out huge volumes of basalt with nothing more than a little shower of hot magma, not a catastrophic eruption. Rhyolite magmas, on the other hand, are very, very viscous. Okay, they don't flow easily. They're erupted, and they pretty much stay put. Believe it or not, this plug right here is actually a rhyolite volcanic eruption. It's a rhyolite magma that was erupted and literally went nowhere. It just sat as this big, viscous, solid goo and cooled right in place. So rhyolite magmas don't flow very far. So as I just said, mafic basalt magmas tend to be very fluid, and they rarely lead to major volcanic explosions. On the other hand, felsic magmas are really viscous, they don't flow, and because of that they tend to be really highly explosive. So for example, Hawaii just keeps gushing magma, but stratovolcanoes like Mount St. Helens in Washington state have experienced huge mega eruptions. So why are these felsic magmas at subduction zones more viscous than their basaltic counterparts? Part of this goes right back to last week's lecture. More felsic magmas tend to form more complex silicate mineral structures. And you might recall that that involves these basic silica tetrahedra sharing oxygen at the corners. And as we build up these long chains of, for example, single chain silicates or big framework silicates, these silicate molecules act as a drag that basically resists flow within the magma and prevents it from flowing, makes it sticky. The second reason is that felsic magmas tend to exist and be erupted at lower temperatures. And this goes right back to Bowen's reaction series, which we saw in the last class also. If you look, these mafic minerals crystallize at high temperature. So a basalt would actually cool to a rock up around 1,000 degrees or so, whereas a felsic rhyolite magma actually might not completely cool to a rock until about 750 degrees C. So because the magma can exist at a lower temperature, it tends to be more viscous and kind of stickier at that lower temperature. Generally, hotter fluids are more fluid, and cooler fluids tend to be more viscous. So in the last part of this lecture, let's look at how these differences in viscosity between basalt and rhyolite magmas actually directly influence the properties of shield volcanoes and stratovolcanoes. So the first thing to know is that the fluid basalt magma creates what's called a shield volcano. And the name implies just what it is. It's a broad volcanic dome that might have, a diameter of 100 kilometers or hundreds of kilometers, really, really broad. And the reason it's broad is because the basalt lava flows that are erupted, they flow long distances, and they'll flow even down a very low gradient, all the way out to the ocean in this case. And so as these lava flows keep flowing away in a radial direction, we end up with this broad shield volcano with very low angle, shallow slopes. Okay? So that's a shield volcano associated with basalt magmas. In contrast, those rhyolite lava flows are very viscous, right? They don't flow very far. And the result of that is that they get erupted and they end up just going a very short distance down the slope and then cooling and solidifying. And so the end result is that we build up flow on top of flow right near the main volcanic vent, and we end up with a very steep volcano because those flows are unable to reach out to the edges. So these are called stratovolcanoes, and they all tend to have this really unique kind of cone shape with the very steep flanks. For example, here's a few stratovolcanoes that are associated with subduction zones around the edge of the Pacific. Mount Shasta, 14,000 foot peak in Northern California. Mount Fuji we've already seen. Here's Mount Shishaldin in Alaska in the Aleutian volcanic arc. They all have that cone shape associated with stratovolcanoes. Just to hit that home once more, where will you find these things? You'll find stratovolcanoes in what's called the Ring of Fire, or basically this ring around the Pacific Ocean where subduction zones exist. And we've already pointed some of this out, but you'll find these stratovolcanoes associated with subduction zones all around the edge of the Pacific, whether it's in the South Pacific or the Aleutians or South America. Now, stratovolcanoes are much more explosive. We've said that already, but why? The main reason is because the magma is much more viscous, and that it's much harder for gases or volatiles to escape from the magma. So that includes things like carbon dioxide, water vapor, sulfur dioxide. These volatiles end up trapped in bubbles within the magma, and they literally are not able to escape. So what happens is pressure builds up within the volcano, and eventually that gas pressure actually causes this catastrophic explosion, something like a balloon popping. And of course we now shower ash and particles into the air. And so what are some of the products associated with this stratovolcano eruption? Here's a lava bomb, a hot piece of lava that might come flying through the air at you. Of course, a lot of ash and pumice can become in all different sizes, including ash clouds that can stay airborne for weeks to months in the sky. Lava flows, of course, although the lava doesn't flow as far in a stratovolcano, it's still, a lot of it comes out during an eruption. And then all of this stuff kind of combines to what's called a pyroclastic flow. And this is a very unique feature of a stratovolcano. A pyroclastic flow is basically a mixture of ash and gases and volcanic bombs. And the force of the blast initially keeps all these particles kind of mixed in this huge mixture, a very turbulent, a lot of energy, and gravity pulls the whole mixture down the hill in this kind of roaring slide of material. And so this can directly overtake structures and infrastructure and destroy it. And then, of course, also eventually this higher ash cloud will settle down on top also. So this could definitely sweep you off your feet. It would also, of course, burn you, and then it would bury you in ash. So we know this happens because we've observed it many times in stratovolcanoes. But also in the geologic record, we find the rock that is actually formed from these pyroclastic flows. And this is called an ash flow tuff. Here's a couple examples outside of Yellowstone. And what you see here are these thick beds. You've got some coarser material on the bottom, some of those big bombs and clasts. And then above that is some of the finer ash that's settled out a little later. The whole thing, of course, was hot, so there continued to be some melting and crystal growth, and then eventually it cools and welds into a solid rock. So that's called an ash flow tuff, and this is one of the ways we know about past eruptions. Great, so I'd like to hit home the idea of a pyroclastic flow by having you guys watch a couple quick YouTube videos that show examples of pyroclastic flow and also a pyroclastic ash cloud. Unfortunately, I can't play these directly within my video because it's a copyright violation on YouTube, so you'll have to follow these links to actually go find these videos. So this first link I'll show you is a video of Unzen volcano. So you could probably just go to YouTube and search Unzen volcano and watch it. It's about 1 minute and 12 seconds long. The second video is Japan's Mount Ontake. So you could probably just search that and you'll find this video about 1 minute 29 long of these people being caught in an ash cloud. Great. So go ahead and watch those videos quickly and then rejoin me. Okay, so I think that provides a pretty clear evidence for why volcanoes are relevant to human life and are a pretty major hazard. So with that in mind, let's return to our question that we posed at the beginning of the lecture. That was, which of these towns is in more danger from its nearby volcano? We had Mount Arenal in Costa Rica, and we had Mauna Loa in Hawaii. And we said at the outset that the dangers are different to the two towns. And I hope now you have some sense of why the dangers are different. Of course, the Arenal volcano is near a subduction, is formed above a subduction zone off the coast of Costa Rica. So it is a felsic stratovolcano that is likely to erupt catastrophically with a big pyroclastic flow. Whereas in contrast, Mauna Loa is a hotspot volcano that's going to erupt mafic magmas like basalt. It's unlikely to have a violent catastrophic eruption. Instead, those fluid mafic lava flows are likely to flow long distances, potentially damaging helo. So we won't get the pyroclastic flow, but we might get some dangerous lava flows here. So I'll leave you with these 4 concept questions. Remind you, you don't need to know the answer to these now necessarily, but they will be used as exam questions in the future. Next video, in the next class, we'll look at faults and earthquakes. And of course, please follow this link to take the Moodle exam. Thanks very much. See you in class.